Hello and welcome to my talk. This is Jiaqi Liu from University of California, San Diego. Today, I'm going to talk about a Yaglom-type asymptotic result for subcritical branching Brownian motion with absorption. Let me begin by introducing the model. Starting at x in the positive real line, a particle moves according to standard Brownian motion with drift negative rho and is killed upon hitting the origin. With rate 1, this particle undergoes dialectic branching. Each offspring independently repeats above process, and the system goes on. Here is a picture of the process. We begin with one red particle at time 0. This particle moves according to Brownian motion with drift for an exponentially distributed time. Then this particle divides into two particles, a red one and a blue one. Those two particles move independently according to Brownian motion with drift until either they branch or hitting the origin. So you can see the blue particle is killed at the origin before branching, while the red particle after some time gives birth to two particles, a yellow one and a red one, and the system moves on. The natural question following the model is whether the process becomes extinct or some particles survive forever. This question was answered by Kasten's original paper in 1978. Kasten showed that when rho, the negative drift, is greater or equal to square root of 2, branching Brownian motion with absorption dies out almost surely, while when rho is less than square root of 2, there is a positive probability of survival. Therefore, rho equals square root 2 is a critical value. In this talk, we'll focus on the subcritical and critical cases. There has been a long-standing interest in problems related to the asymptotic behavior of the survival probability. We know that in subcritical and critical cases, the process dies out almost surely. But what is the probability that the process survives up to a large time t? Furthermore, conditional survival up to an unusually large time t, what's the behavior of the process? This type of result is called Yaglom-type theorems after Yaglom's work pertaining to critical Galton-Watson processes. These two questions have been studied extensively by multiple papers, and our paper, based on the results of the first two questions, aims to find out the long-run behavior of the process conditional survival as the process gets closer to being critical. In the next several slides, I'm going to present several results pertaining to the first two questions in the critical and subcritical cases, respectively. In the critical case, Kasten obtained upper and lower bounds on the long-run survival probability. In 2014, Julian Baristiki, Nathaniel Baristiki, and Jason Schwansberg further improved Kasten's result. Let zeta be the extinction time. If we start the process from a single particle at x, then they prove that the probability that the process survives up to time t is bounded above and below by those two quantities. So basically, the long-run survival probability looks like x times e to the square root 2 of x minus 3 pi squared t to the power of 1/3. We also have a Yaglom-type result. Let n of t be the number of particles at time t. Kasten shows that if we again start the process from a single particle at x, then if we condition on survival up to a large time t, the probability that the number of particles at time t exceeds a constant times t to the 2/9 times log t to the 2/3 goes to 0 as t goes to infinite. In subcritical case, John Harris and Simon Harris obtained similar results in their 2007 paper. Let P sub x sub negative rho be the probability measure for branching Brownian motion with absorption starting from a single particle at positive x with drift negative rho. We want to write rho in terms of a positive number epsilon. Let rho equal square root 2 plus 2 epsilon. Let zeta be the extinction time. Let n sub negative rho sub t be the number of particles at time t under the probability measure for branching Brownian motion with absorption. Harris and Harris prove that for rho greater than square root 2 and positive x, there exists a constant k epsilon that is independent of the starting position x, but dependent on the drift, and therefore on epsilon, such that as t goes to infinite, the probability that the process survives up to time t is roughly of the order of this constant k epsilon times x times t to the negative 3/2 times e to the rho x minus epsilon t. Furthermore, they show that as t goes to infinite, the ratio between the probability that the process survives up to time t and the expected number of particles at time t goes to 1/2 rho squared times the same constant k epsilon. The Yaglom type results follows from the limit estimate of the long-run survival probability. In the same paper, Harris and Harris pointed out that for rho greater than square root 2 and positive x, there is a probability distribution pi such that the limit as t goes to infinite, condition on survival up to time t, the probability that the number of particles at time t is j goes to pi j. Moreover, one can easily compute the conditional expectation. Condition on survival up to time t, the expected number of particles at time t goes to 2/rho squared times k epsilon. As you can see, the constant k epsilon plays an important role in calculating the limiting expected number of particles alive condition on survival in the near critical case. Based on previous work, I'm going to state my main result. Again, we want to write rho in terms of a positive number epsilon, but this time we focus on the case when epsilon is arbitrarily small. Let rho equals square root 2 plus 2 epsilon. We show that the long-run expected number of particles conditioned on survival grows exponentially as the process gets closer to being critical. To be more precise, there exist positive constants C1 and C2, such that for epsilon small enough, the limit of the expected number of particles at time t conditioned on survival is bounded above and below by e to the constant over square root of epsilon. Note that these two constants, C1 and C2, does not depend on the starting position x. The proof of the main result relies on a better understanding of the constant k epsilon appearing in Harris and Harris papers as the drift approaches the critical value. According to the Yaglom type result in their paper, studying k epsilon boils down to finding an asymptotic expression for the survival probability in the slightly subcritical regime. Here, we apply a spinal decomposition to transform survival probability to expectation of the reciprocal of a martingale. This spinal decomposition was first introduced in Harris and Harris paper in 2007. First, let me define a numeric Qx based on an additive martingale. For a particle U survive at time s, let YUS be its position at time t. We define the Radon-Nikodym derivative between the new measure Qx and the original probability measure for the Brownian motion with absorption at time s to be the summation of all u's yu of s e to the rho yu of s plus epsilon s. Harris and Harris pointed out that under the new measure Qx, the spine moves as a space-3 process starting from x. With accelerated rate 2, the initial ancestor undergoes binary fission. The spine is chosen uniformly from the two offspring, and the remaining offspring initiates an independent copy of the original Brownian motion with absorption. As a result, the reciprocal of the expected number of particles survive at time t, conditioned on survival until time t, can be expressed as a polynomial of t times the expectation of the reciprocal of a p supermartingale under the new measure Q. So the main result can be proved by computing the upper and lower bounds of this expectation under the measure Q. Let me mention that this paper is available on arXiv. Finally, I would like to express my deepest appreciation to my advisor, Professor Jason Schwansberg, for his support during the planning and development of this paper. I would also like to acknowledge the support of the National Science Foundation for funding this study. Thank you very much for your attention.